Good day. I welcome you all in this lecture on water demand of the subject environmental engineering as per the syllabus suggested by Maulana Abul Kalam Azad University of Technology. The subject code is CE701 and the module number is 1. Myself Sandeepan Saha, Assistant Professor for the Department of Civil Engineering of Greater Kolkata College of Engineering and Management, GIS Group. Now let us first proceed to have a look on the topics that we are going to cover in this lecture. That is water demands, per capita demand, variations in demand, factors affecting demand, design period, and population forecasting. Water supply system is the infrastructure for the collection, transmission, treatment, storage, and distribution of water for homes, commercial establishments, industry, and irrigation, as well as for such public needs as firefighting and street flushing. Of all municipal services, provision of potable water is perhaps the most vital. Potable water, also known as the drinking water, is a water that does not represent any significant risk to health over a lifetime of consumption, including different sensitivities that may occur between life stages, as defined by the World Health Organization 2017 report. The World Health Organization considers access to safe drinking water a basic human right. About 1 to 2 billion people lack safe drinking water, a problem that causes 30,000 deaths each week. More people die from unsafe water than from war, as stated by UN Secretary General Ban Ki-moon in 2010. So, as you can see, people depend on water for drinking, cooking, washing, carrying away wastes, and other domestic needs. Water supply systems so need to meet requirements for public, commercial, and industrial activities. In all cases, the water must fulfill both quality and quantity requirements. Let us proceed to the quantity aspect of water supply, which is also known as the demand for water or simply water demand. If a total volume of water, that is V, liters or million liters, is supplied to a place annually, then the daily average supply is V by 365. That means the total volume of water V is divided by the 365 number of days, as a year consists of only 365 days. Henceforth, the daily average supply of water per head, which is also known as per capita demand, expressed as small q, can be calculated as V by 365, which is already we know that is the daily total supply of water, which has to be divided by the total number of heads. So basically, this amount of water needs to be supplied for each head daily to meet the daily needs, that is drinking, for cooking, for washing, etc. The per capita demand, which is also known as the rate of demand or simply LPCD. LPCD stands for liter per capita demand or liter per capita demand or liter per day per head. As we know that the per capita demand is the amount of water needed per head on a daily basis for various daily needs, but this amount varies depending upon certain various factors, which are as follows. The first one is size of the city. Per capita demand for big cities is generally large as compared to that for smaller towns, as big cities have sewered houses, presence of industries. If industry is high at a certain place, then definitely water demand is high, as to run a certain industry, requirement of water is high. Then comes the climatic conditions. If it is hot climate out there, requirement of water is high. Now the habits of people and their economic status. As the areas with higher incomes generally use more water than areas with low incomes. Larger landscaped residentials lot that require more water are often associated with more affluent communities. Additionally, higher income households may be less sensitive to the cost of water since it represents a very smaller portion of household income. Now the factor is quality of water. If water is aesthetically and medically safe, then the consumption will increase as people will not resort to private wells. The next important factor is pressure in the distribution system. If the pressure is high in the water distribution system, that means supply of water is great and high, which is automatically turned out to be the reason for high water demand. Now comes the another important factor is which is efficiency of water works administration. Leaks in water mains and services and unauthorized use of water can be kept to a minimum by regular checks and surveys. The last important factor in our list is cost of water. Water prices can influence demand of water by providing a monetary incentive for customers to conserve water. Rate structures have been established in many places to incentivize the water conservation concept, but the effectiveness of these rate structures to determine the excessive use and customer sensitivity to water prices may vary. There are several types of water demands which a city may have and may be divided into the following types: domestic water demand, industrial and commercial water demand, demand for public uses, fire demand, water required compensating losses in wastes and thefts. The first one is the domestic water demand. This is the amount of water required in private buildings for drinking, cooking, bathing, lawn sprinkling, gardening, sanitary purposes, etc. This amount varies according to the living conditions of the consumers. On an average, this domestic consumption under normal conditions in an Indian city is expected to be around 135 liters per day per person, as per the Indian Standard 1172 of 1971. The total domestic consumption generally amounts to 50 to 60% of the total water consumption. As it is already mentioned that an average daily consumption under normal conditions in an Indian city is expected to be around 135 liters per day per person. Here is the details usage list of 135 liters per day per person, which is as follows. For drinking purposes, around 5 LPCD amount of water is required. LPCD means liter per capita demand. For cooking purposes, 5 LPCD is required. For bathing purposes, around 55 LPCD is required. For washing of clothes, 20 LPCD of water is required. Washing of utensils, 10 LPCD of water is required. And for washing and cleaning of houses, 10 LPCD of water supply is required. And for the washing and cleaning of residences, 30 LPCD of water supply is required. Altogether, the daily domestic water consumption is around 135 LPCD, that is 135 liter per capita demand, which is required for the daily purposes per head. Please keep that in mind that this 135 LPCD is required for per head purpose on a daily basis. The following table deals with the average domestic water consumption per head in an Indian city based on the total number of population. The first one is for the communities with population up to 20,000 and without flushing system, and it can be categorized into two parts. The first one is where water is supplied through stand post, and in this case the required amount of water supply is 40 LPCD. And the second part is where the water is supplied through house service connections, and in this case around 70 to 100 LPCD amount of water is required. The next is for the communities with population in between 20,000 to 1 lakh with having full flushing system, and in this case the required water demand is around 100 to 150 LPCD. And the third one is for the communities where the population is more than 1 lakh having full flushing system, and for this case the required water demand is around 150 to 200 LPCD. As you can understand that with increasing number of populations, the requirement of water demand is getting higher. Here is the point to be noted that the values of water supply given as 150 to 200 liter per day per head, that is, I am talking about this thing, this portion. This may be reduced to 135 liters per head per day for houses for lower income groups and economically weaker sections of society, depending upon prevailing conditions. And this information has been acquired from the code, that is Indian Standard of 1172 of the year 1993. The following table depicts the daily average domestic water consumption per head in an Indian city based on the type of city. The first one type is towns provided with pipe water supply but without sewerage system, and for this case the required and recommended water supply is 70 LPCD. The second one is the cities provided with piped water supply and where sewerage system is either existing or contemplated, and for this case the recommended water supply is around 135 LPCD. And the third case is for the metropolitan and mega cities provided with piped water supply where sewerage system is either existing or contemplated, and for this case the recommended water supply is around 150 LPCD. There is a point to be noted that in urban area where water is provided through public stand posts, for this case 40 LPCD should be considered as water supply, and this information has been acquired from the Manual on Water Supply and Treatment, May 1919, as suggested by the Central Public Health and Environmental Engineering Organization, that is CPHEEO. Let us have a look at the water demand required for the industrial and commercial purposes, and this includes the quantity of water required to be supplied to the offices, factories, different industries, hospitals, hostels, etc. And these kind of buildings can be categorized under the industrial and commercial purposes. This water demand will vary considerably under the nature of the city and with the number and types of industries and commercial establishment. But there is no direct relationship of the consumption with the population, and hence the actual requirements for all industries should be estimated. The water requirements for buildings other than the residences as per IS 1172 of 1973 standards are as follows. Here I have mentioned several industrial and commercial institutes, and here the list of water requirements as per the IS 1172 of 1973 standards for commercial and industrial purposes. The first one is hospital. Having bed number more than 100, the required water supply is 450 liter per bed per day. So it's not measured in liters per head per day. And the hospitals having beds less than 100, the required water demand is 340 liter per bed. For hotels, the required water supply or water demand is 180 liter per bed per day. So you can see that for the first three cases, the water supply is measured in liter per bed per day, but not in liters per head per day. Now we come to the hostels, and for this purpose the required water supply or water demand is 135 liter per day per head. For nurses' homes and medical quarters, the required water supply is 135 LPCD. For boarding schools or colleges, the required water supply or water demand is 135 LPCD. For restaurants, the required water supply is 70 liter per day per seat, not LPCD. For airports and seaports, the required water supply is or water demand is 70 LPCD. For junction stations and intermediate stations where mail or express stoppage is provided, the required water supply is 70 LPCD. For terminal stations, the required water supply is 45 LPCD. And for the intermediate stations, the required water supply is 45 LPCD. For the day schools or colleges, the required water supply is or water demand is 45 LPCD. For offices, the required water supply is 45 LPCD. And for the factories, the required water supply is 45 LPCD. If there is no bathroom is provided, then this particular 45 LPCD amount can be reduced to 30 LPCD for the case of factories. And for the institutes or buildings like cinema, concert halls and theaters, the required water demand is 15 LPCD. Here, specifically, the water demand for various transportation centers has been discussed, as transportation centers are important commercial institutions. Here, the transportation centers are categorized into two different sectors. The first one is railways, bus stations and seaports, and the second one is airports. The first one, that is the railways, bus stations and seaports, are further categorized into three different types. The first type is intermediate stations, excluding mail and express stops. In this case, the required water demand is 45 LPCD, where bathing facilities are provided, and 25 LPCD, where bathing facilities are not provided. In case of junction stations and intermediate stations, where mail or express stoppage is provided, the required LPCD, the required water demand is 70 LPCD for bathing facilities are provided, and if bathing facilities are not provided, then the required water demand is 45 LPCD. And for the terminal stations, if bathing facilities are provided, then the required water demand is 45 LPCD, and if no bathing facilities are provided, then the required water demand is 45 LPCD. And the second important category is airports. For both the international and domestic airports, the required water demand is 70 LPCD, where bathing facilities are provided, and 70 LPCD where no bathing facilities are provided. And these informations are acquired from the Code of Basic Requirements for Water Supply, Drainage and Sanitation of IS 1172 of 1993. Now, let us come to the demand of water for public users. This includes the quantity of water required for public parks, gardening, washing and sprinkling on roads, use in public fountains, etc. A nominal amount not exceeding 5% of the total consumption may be added to meet this demand on an arbitrary basis, or else the consumption of water for municipal purposes can be considered as given below. For public purpose, for the purpose of public parks, the water consumption can be considered around 1.4 liters per meter square per day. For road watering, the water consumption can be considered as in between 1 to 1.5 liters per meter square per day. And for sewer cleaning purpose, the water consumption can be considered as 4.5 liters per head per day. Now let's come to the firefighting demand. Extinguishing for fire is very small in a year, but the rate of consumption is large. The scheme should provide the necessary peak demand of water for firefighting. The water requirements for extinguishing fire depends on bulk, congestion and fire resistance of buildings. Indirectly, we can say it mainly depends on the population. The minimum limit of fire demand is the amount and rate of supply that are required to extinguish the largest probable fire that may occur in a town. The per capita fire demand is very less on an average basis, but the rate at which the water is required is very large. The rate of fire demand is sometimes treated as a function of population and is worked out from the following empirical formulas. These formulas are standardized by various international authorities. The first one is the American insurance formula. As you can see, the formula is Q equals to 4637 root over P multiplied by 1 minus 0.01 root over P, where Q is the required supply rate of water during firefighting measured in liter per minute, and P is the population measured in thousand. Suppose a sector has a population of 1 lakh. Then putting the value of P in the formula, we are putting the value of P in this formula, and then we can get the required supply rate of water, that is 41760 liter per minute. There are other formulas like Cushing's formula, Freeman's formula, Ministry of Urban Development manual formula, where putting values of P, that is population, we get the required firefighting demand. Here, as for the Ministry of Urban Development manual formula, this formula is applicable where the population is more than 50,000, and Q, that is the supply rate of water during firefighting, is measured in kiloliters per day. Now let us have a look on the water demand required for compensating losses in wastes and thefts Gross water demand for the project service area can be computed by adding the domestic and non-domestic water demand assessed and also considering the losses in the water treatment plants, transmission mains, and the local distribution networks. Present day leakage losses in the local distribution networks in most of the Indian cities are very high. In a few typical cases, 40% of the losses have been reported. In major metro cities, leakage monitoring operations and repairs to reduce leakages are in the ongoing stage, and future water demand projections should consider reduced leakages as the consequences of the above activities. In any case, it would be almost impossible to have financially viable projects if the future leakages are not controlled by above mentioned measures. A typical future target could be 15% losses in the local distribution network, which could be considered in projecting the gross water demand, though at times the financial institutions might prefer 10%. Fluctuations in rate of demand. As we have already discussed that the average daily per capita demand equals to the quantity required in 12 months divided by 365 days divided by the total number of population. If this average demand is supplied at all the times, it will not be sufficient to meet the fluctuations as follows. Seasonal variation. The demand peaks during summer. Fire breakouts are generally more in summer, increasing demand. So there is seasonal variation. Daily variation. It depends on the activity. People draw out more water on Sundays and festival days, thus increasing demand on these days. Hourly variations. These are very important as they have a wide range. During active household working hours, that is from 6 to 10 am in the morning and 4 to 8 pm in the evening, the bulk of the daily requirement is taken. During other hours, the requirement is negligible or not that much. Moreover, if a fire breaks out, a huge quantity of water is required to be supplied during a very short time, necessitating the need for a maximum rate of hourly supply. An adequate quantity of water must be available to meet the peak demand. To meet all the fluctuations, the supply pipes, service reservoirs, and distribution pipes must be properly proportioned. The water is supplied by pumping directly, and the pumps and the distribution system must be designed to meet the peak demand. The effect of monthly variation influences the design of storage reservoirs, and the hourly variations influences the design of pumps and service reservoirs. As the population decreases, the fluctuation rate increases. The maximum daily demand can be computed as this formula, that is 1.8 times the average daily demand, and the maximum hourly demand of maximum day, there is a peak demand, can be calculated as per the following formulas. Now let us have the calculation process of water quantity estimation. The quantity of water required for municipal uses for which the water supply scheme has to be designed requires the following data. Number one is water consumption rate, that is the per capita demand in liters per day per head, and number two is population to be served. So if we do the calculation of multiplication between per capita demand and population, then we get the quantity of water which is to be served to the city or the sector through the water supply scheme. Design periods and population forecasting. These two entities are very important for designing a water supply scheme. The design period should be worked out with due provision for the estimated requirements of the future. The future period for which a provision is made in the water supply scheme is known as the design period. Design period is estimated based on the following. Number one, useful life of the component, considering obsolescence, wear, tear, etc. Number two is expandability aspect. Number three, anticipated rate of growth of population, including industrial, commercial developments and migration immigration. Number four is available resources, and number five is performance of the system during initial period. Population projection and water demand assessment has been an integral part of various feasibility studies, detailed project reports, and master plans being prepared for water supply projects in the urban sector. It is necessary to have inputs of population forecasts for the service area of a project before water demand assessment can be made. There are a number of alternate methods to forecast future population for urban or rural service areas. It is not always possible to make accurate population forecasting except for immediate future. However, it is advisable to use these methods to have alternate population forecasts and then select one of them for use in water demand assessment. It must be remembered that the population forecasts for distant future will lead to a general idea of the overall picture of water supply or sewerage system needed in the long run. The system to be executed will be generally for the initial phase for immediate future for which the population forecasts can be reasonably sound. The overall system identified based on the approximate forecasts of population for distant future allows the designer to ensure that the initial phase system which is going to be executed fits the overall system in the long run. There are various methods adopted for estimating future populations as given below. The particular method to be adopted for a particular case or for a particular city depends largely on the factors discussed in the methods, and the selection is left to the discretion and intelligence of the designer. The population forecasting methods are as follows: arithmetic increase methods, geometric increase method, incremental increase method, decreasing rate of growth method, simple graphical method, comparative graphical method, ratio method, logistic curve method. As we have already understood that the population forecasting is very important for the serviceability and sustainability of a water supply scheme, let us do some numerical problems based on the population forecasting methods as mentioned here. In our current lecture, we will try to concentrate to do the numerical problems based on the arithmetic increase method, geometric increase method, and incremental increase method. First, let us do a numerical problem as per the arithmetic increase method. Let us do a numerical problem on population forecasting as per arithmetic increase method. Here is the problem. The population of 5 decades from 1930 to 1970 are as follows. From 1930 to 1970, the population are given here. So now we have to find out the population at the year 2000. In order to solve the numerical, first we need to calculate the increase in population over the decades. From 1930 to 1940, the increase in population was 28,000 minus 25,000. So it is 3,000. By applying the same method, we can calculate the increase in population from 1940 to 1950. So the increase in population is 6,000, 34,000 minus 28,000. From 1950 to 1960, the increase in population was 8,000, and from 1960 to 1970 the increase in population was 5,000. So the column is increase in population. So the total increase is equals to 22,000 over the four number of decades. That is the number of decades we can find from 1930 to 1940. There is one decade. In between 1940 and 1950, there is one decade, and in between 1950 and 1960, there is another one decade, and the and in between 1960 and 1970, this is another one decade. So now we have to calculate the average increase in population. So we'll get it by dividing the total increase, that is 22,000, divided by the four number of decades. So we get the average increase in population, that is 5,500. Now to calculate the population or to forecast the population in 2000, we need to perform this particular calculation, that is population in 1970 plus number of intervals, rather than I should say it as number of decades between 1970 and 2000 multiplied by x bar, that is the average increase in population. So putting the values of population in 1970, which was as per the given problem, that is 47,000 plus the number of decades between 1970 and 2000 is 3 multiplied by x bar, that is 5,000 and 500. So calculating all together, we get the value of 63,500. So as per the arithmetic increase method, the population in 2000 would be 63,500. Now let us do the same problem by applying the geometric increase method. Now we will try to solve the same problem as per the geometric increase method, and in order to do so, first we need to calculate the increase in population as we have done in the arithmetic increase method. So As we know that the in between the 1930 and 1940, the increase in population was 3,000. From 1940 to 1950, increase was 6,000. From 1950 to 1960, the population increase is 8,000, and in between 1960 and 1970, the population increase was 5,000. So now we have to calculate the percent increase in population, or we call it growth rate. It can be denoted by R. So R1 is calculated by 3,000, that is the population increase in between 1930 and 1940, divided by the population during 1930, that is 25,000, and making it as a percentage, we multiply this by 100%. So we get 12%. So in between 1930 and 1940, the growth rate was 12%. The same process we apply, we get R2, that is the growth rate between 1940 and 1950. And how do we get it? We get this by dividing 6,000 by 28,000 and making it as percentage. We get the growth rate in between 1940 and 1950 as 21.4%. Same we get R3. So we calculate this by dividing 8,000 by the population in 1950, that is 34,000 into 100%. We get the growth rate as 23.5% in between 1950 and 1960, and in between 1960 and 1970, the growth rate we get, that is 11.9%. And how do we get it? By dividing 5,000 by 42,000, that is the population of 1960. We get the growth rate in between 1960 and 1970. So now we have to calculate the geometric mean, that is, how do we have to calculate the geometric mean of geometric mean of the growth rates? And how do we do this? We do this applying the same form, this formula. We have four number of growth rates because there are 4 decades in between 1930 and 1970. So putting the values of R1, R2, R3, R4, we get the geometric mean of the growth rates as 16.37%. So the population in 2000 as per geometric increase method, we have to use this formula, that is population of 1970 multiplied by 1 plus R by 100 whole to the power n. Here R is the value of the geometric mean that we have calculated already, and n stands for number of decades between 1970 and 2000. So applying those values, we get 47,000. That is the population of 1970. 1 plus 16.37 by 100 whole to the power 3, as the number of decades between 1970 and 2000 is 3. So calculating all the values, we get the population of 2000 as 74,000 and 66. So this is the population of 2000 calculated as per the geometric method. Now let us solve the same numerical problem using the incremental increase method. Now we will be solving the same problem by using incremental increase method. In order to do so, first we need to calculate the increase in population over the decades. That is, in between 1930 and 40, the increase in population was 3000, and in between 1940 and 1950, the increase was 6000, and in between 1950 and 1960, the population increase was 8000, and the population increase between 1960 and 1970 was 5000. So further we move to the calculation. Now we will have to calculate the incremental increase. In population. So how do we calculate? We calculate this in case of between 3000 and 6000, there is the incremental increase is in positive side. The incremental increase is in the positive side. That is 3000. We consider this as positive. Again, The next incremental increase calculation is between 6,000 and 8,000. So the incremental increase is 8,000 minus 6,000 equals to 2,000. Again, the incremental increase is in the positive side. But in case of the 8,000 and 5,000, the incremental increase is 5,000 minus 8,000. So it is in the, so the incremental increase in population is in the negative side. So the net incremental increase is equals to 3,000 plus 2,000 minus 3,000, as we can get from here. So we have 2,000. So the average incremental increase equals to 2,000 by 3 decades. That is, the incremental increase can be found in 3 decades. So we have 667, and we denote this as y bar. And here we have the, and from here we can get the average increase in population that is x bar, which is the total increase in the population was 22,000 divided by 4 number of decades, as we can find in between these years, that is from 1930, in between 1930 and 1970, we have 4 number of decades. So dividing 22,000 by 4 number of decades, we get x bar equals to, that is the average increase in population was 5,500. Now in order to calculate the population in 2000 as per the incremental increase method, we need to apply this following formula, that is population of 1970 plus nx bar plus n multiplied by n plus 1 by 2 into y bar. Here x bar, sorry, n equals to number of decades between 1970 and 2000. So we have the population in 1970, that is 47,000, plus n equals to 3 as the number of population, sorry, the number of decades between 1970 and 2000 is 3 multiplied by x bar, that is 5,000. We have got this from here, plus n equals to 3, that is number of decades between 1970 and 2000, multiplied by 3 plus 1 divided by 2, and y bar, that is 667. We got this from here. So calculating all together, we get the population in 2000 as per the incremental increase method is 67,000 and 502. So the population of 2000 as per the incremental increase method is 67,000 and 502. In this lecture, we have studied details of water demand along with the various population forecasting methods, which are very important for designing a water supply scheme. Thank you.